Luckily, we get to go through them pretty slowly. I don't think this section's super difficult, but as you notice, with your 5 lovely theorems, there's a lot. There's a lot in here. It's not difficult stuff, but kind of a lot of things to go through. So, section 6.2 is properties of parallelograms. So first thing, let's talk about what a parallelogram is. Probably heard the word before. Maybe know what it is, maybe not. A parallelogram, first of all, it's a quadrilateral, so a 4-sided figure, that has both sets of opposite sides that are parallel. So if you look at this figure right here, this is a parallelogram. So this top is going to be parallel with the bottom, and then the left side is going to be parallel, to the right side. Okay? Those are what we call the opposite sides, okay? Top, bottom, right, left. They're going to be parallel to each other. Now, out of these 5 theorems that you copied down, some of them talk about opposite angles. Opposite angles. Okay, so the opposite angles. If I'm looking at the bottom left angle in the parallelogram, the opposite angle to that one would be the top right angle. Or you could do the top left and the bottom right. Okay, but they're going to be on opposite sides of the parallelogram. And then the last type of angle that these theorems talk about is consecutive angles. So consecutive angles, I kind of think of it, they're like right next to each other. So for example, this angle is consecutive to this angle. But that's not the only set of consecutive angles. You could have the top 2 angles. They're next to each other. The bottom 2 angles, or the 2 angles on the right-hand side. So pretty much if they're not opposite angles, they're going to be consecutive angles. If they're not consecutive, they're going to be opposite. Okay? So keep that in mind as we go through these theorems. So these theorems, all of them, except the last one, are saying, okay, if a shape is a parallelogram. So I have a shape. I know it's a parallelogram. Here's some things that these theorems tell us. So the first one, if a quadrilateral is a parallelogram, then the opposite sides are not only parallel, they're congruent. So they're the same length. So I think this gets a little tricky because I've talked to you over and over and over again that people oftentimes mistake just because they're parallel, any parallel lines, like, oh, they're congruent. That's not true. Just because things are parallel doesn't mean they're congruent. But it turns out in a parallelogram, yes, they are. They are parallel and they are congruent because it's a parallelogram. Okay, so the top is congruent to the bottom, the left is parallel, or congruent to the right side. Okay, another theorem, theorem 6.4. If a quadrilateral is a parallelogram, then the consecutive angles, so remember the angles that are side by side, they're supplementary. So you can add any 2 pairs of the consecutive angles, and they would equal 180. So A and B are consecutive angles, so if you took the measure of angle A plus the measure of angle B, you get 180. If you took B plus C, you get 180. If you took C plus D, you get 180. And if you took D plus A, you get 180. Any pairs of consecutive angles are supplementary. That's going to be really useful for some of the things we do today. And then the last one up here talks about the opposite angles. So either the top left and bottom right, or the top right and bottom left. Opposite angles in a parallelogram are congruent. So consecutive angles are supplementary. I kind of think about this. Consecutive angles are kind of like same side interior angles, which is actually exactly what they are. And these aren't necessarily like alternate interior, but kind of that's how you end up proving it in a way. But right, opposite sides. Okay, those are going to be congruent. Okay, so we can use these theorems to find some missing angle measures. So if they say I want to find the measure of angle R in parallelogram RSTU, so if I have angle S, I'm looking for angle R. Angle S and angle R are consecutive angles. They're right next to each other, so I know they're supplementary. So how would I find the measure of angle R? They're supplementary, so I would take 180 minus 71. I would get 109. Okay, we'll come back to this example after we talk about that bottom one right there. Theorem 6.6, maybe should have thrown that up there. It talks about, once again, have a quadrilateral, okay? What you can do with the quadrilateral is you can draw the diagonals. So the diagonals are going to connect the opposite vertices. So you would draw a line from B to D and from C to A. Okay, what happens here, when you have a quadrilateral and you draw the diagonals, those diagonals are going to bisect each other. So remember, bisect means cuts in half. But you have to be really careful here about what segments are going to be congruent to what segments. Okay? This diagonal BD right here is being cut in half. That's what's being cut in half by the other diagonal. So these two segments are congruent. Okay? And then this diagonal, AC, is being cut in half by BD, so those two segments are congruent. So the diagonal is what's being cut in half. Okay? And then the last theorem doesn't deal with parallelograms, but it does talk about parallel lines. So it says if you have 3 or more parallel lines, so it kind of starts with 3, but if I added another parallel line down here and another one and did 4 or 5, it would be the same thing. So you have these 3 parallel lines marked that way, and you have a transversal. Now what happens with these parallel lines and the transversal, if you have parallel lines cut by a transversal, and the transversal is cut into congruent segments. So that's kind of like the initial information. So I've got these parallel lines. On this transversal, the parallel lines make AC and CE congruent. Okay, so that's the original information. If that's true, then any other transversal is also going to be cut into congruent segments. Now, what that means is that this transversal is going to be cut into congruent segments here and here. So you can see that marked over here. B, D, and DF are going to be congruent. So don't get that confused with AC congruent to BD. That's not what it's saying. It's saying if these are congruent, then those are going to be congruent. Or you could even draw another transversal there. And if it started out saying, okay, these are parallel lines, these are congruent, well, those segments are going to be congruent. Okay? Like I said, not super difficult stuff, but it's just kind of a lot. So if we apply this last theorem to this problem right here, it says in the figure below, RW is parallel to SV. So if we wanted to mark that, we could. And then SV is parallel to TU. If you remember from a couple chapters ago, we had a theorem that said, if this line is parallel to this line, and this line is parallel to this line, then this line is parallel to this line, they're all parallel. Okay, you can tie that together. So these are all 3 parallel lines. It says that RS equals ST, which means they're congruent. And it says they equal 5. So both of those are going to equal 5. And it says WV equals 7. I want to find WU. So this entire side here. Now notice I have 3 lines, 3 parallel lines cut by a transversal. And when it does that, it creates congruent segments, which means these 2 segments are also congruent. So if WV is 7, what's VU? Also 7, and I'm looking for WU. Yeah, 14. Okay, questions on any of that? Okay, let's get this glued into page 5. This is section 6.2, and it is properties of parallelograms. Alright, so we have lots of drawing to do today, lots of parallelograms. Remember, whenever you're drawing the parallelograms, both sets of sides are parallel and congruent. I know that from that first theorem there. So number 1, let's draw a parallelogram the best you can. Doesn't have to be perfect. Okay, I've got this parallelogram. I want to find x in each parallelogram. So for this one, let's say this bottom left-hand angle is 68 and the top angle is x. Now to find x, I've got different relationships with the different angles depending on which ones you have. What kind of angles would you call x and 68? Same side or not opposite? Consecutive, that's what I was looking for. I'm okay if you want to think of it as same side, because you're going to do the same thing, because if these were same side interior angles, they're supplementary. Same thing with the consecutive angles. They are supplementary. So to find x, we would take 180 minus 68. We should get 112. Okay, let's try another one. We've got this nice little parallelogram here. And the bottom left-hand angle is 82. And then the right-hand angle is x. Now remember, the consecutive angles don't have to be on the left-hand side. They don't even have to be on the right-hand side. They could be the top or they could be the bottom. They just have to be right next to each other. Okay? So this is the same thing. They are supplementary, which means to find x, I would take 180 minus 82, and I should get 98. Questions on 1 or 2? Okay, these next two problems are probably the hardest of them. Not because I think they're super hard problems, just because it's something from algebra that it's been a while since we've done before. So let's start with drawing, not number 2, number 3. Drawing a parallelogram PQRS. So we'll call the top left P, Q, R, S. And then we're actually going to draw the diagonals of this parallelogram. So we're going to connect P and R, and we're going to connect Q and S. Now, before I give you any more information, and actually solve for an x and a y to solve for, I have a parallelogram, and I have diagonals. What do I know about the diagonals of a parallelogram? Leo?
They bisect each other.
They bisect each other. So, I know, without giving you any other information, I know that this segment's congruent to this segment, and I know that this segment is congruent to this segment. So, using that information, if I tell you that that segment is x, this one is y, this is going to be 2y minus 8, and then that last one's going to be x plus 2. Okay, now, it might throw you off right off the bat because I think you're kind of like thinking ahead a little bit. But what I need to do here is I need to set up an equation with some of the information that I have. I know I have congruent segments, so use that idea of these segments are congruent to write an equation. What's one equation we could write? Do what? Now keep in mind that these aren't angles, these are segments, right? So if I know these are congruent, what does that mean? They're what? They're equal, yeah, they're equal. I know that x plus 2 equals y, and I get why you guys are like, oh, I can't solve that one. We'll get to that, okay? What's the other equation I could write? X equals 2y minus 8. Now, I get it. You guys are like, well, that doesn't help anything because I can't solve for x if there's an x and a y. Yes, I can because I have two equations. This is a system of equations. You did this last year. We actually did it a couple of chapters ago, but we went through it really, really fast, and luckily today we have the time. So let's review how to solve a system of equations. Luckily, the systems of equations you're going to have to solve in this section and in this chapter are going to be pretty simple. You should be able to solve them all by substitution. So as a reminder how substitution works. This first equation says x plus 2 equals y, which is important. Because if y equals x plus 2, it means that these two things are the same. They're equal. That's exactly what equals means. Well, if they're the same thing, it doesn't matter if I use y or if I use x plus 2. Because they're the same. So in the second equation, I don't have to use y. I can use x plus 2. So you're going to take that second equation and you're going to rewrite it. You're going to say x equals 2, but instead of y, that first equation tells me that y equals x plus 2. So I'm going to substitute x plus 2 in right there. Now, don't forget that second equation still has that minus 8. So you're not going to change anything about that second equation except for the y. You're swapping out the y for an x plus 2. Now, if you look at this equation, see I only have x's? Okay, so we can solve for x, so distribute your 2. So x equals 2x plus 4 minus 8. So x equals 2x minus 4. Get your x's together, so subtract 2x from both sides. So if negative x equals negative 4, then x equals 4. And once you know what x is, how do you find out what y is? Good. Plug it in. I'd probably plug it into that one. So y equals 4 plus 2. So y equals 6. So I know it's been a while since we've done systems of equations. I know we did it a couple chapters ago, but we kind of zoomed right through it. But the systems of equations you're going to be asked to solve should be pretty simple, and pretty similar to this. Let's try another one of those. Number 4. Okay, number 4, got our parallelogram, and we're going to have Q, R, S, and we're going to draw the diagonals again. Okay, and let's say this segment is y, this segment is 6x, this one is 3x, and then that last one is y plus 12. So, super similar to the last one, I need to represent 2 equations with this information that I have. So, what would one equation look like? Okay, y equals, which one? Be this one, right? Remember what it does is that the diagonals bisect each other. So this is the midpoint of that segment. So y equals 3x, and then what's the other one? 6x equals y plus 12. Now, if you look at the first equation, it says that y equals 3x. So y and 3x are the same thing. So you can use y, or I can use 3x. So in that second equation, we're going to do 6x equals, but instead of y, that first equation tells me that I can use 3x because they're the same thing. So we're going to do 3x plus 12. Get your x's on the same side, so subtract 3x from both sides. So we have 3x equals 12. So x equals 4. Just like the last one, take that value and plug it in. So y equals 3 times 4. So y equals 12. That's probably the hardest thing in this section that you have to do, and it's not even the geometry part, it's the algebra part, solving the systems of equations. Questions on either of those two? Okay. Okay, so this, we're going to draw, okay, I want you to draw 3 parallel lines. 3 parallel lines. If you want to go ahead and mark them with the parallel symbol, might not be a bad idea. And then we're going to draw 2 transversals. 2 transversals through it. Like this. Now, without giving you any more information, well, I guess I need to give you probably a little more information. Let's label these intersections. So this is going to be L, M, N, and then T, U, V. And then let's say ML is 4.5. UV is 3.8. Now, if we take in all that information that they gave us, okay, we know they're parallel because it's marked as parallel. I have these transversals here. They tell me that TU is congruent, or I guess equal, which means they're congruent to UV. So I have these parallel lines cut by a transversal, and on this transversal, it creates congruent segments. What does that tell me? Yeah, these are congruent. Now remember, it doesn't mean that these are congruent to these segments. It means this segment's congruent to this segment. So be careful on that one. Okay? So for number 5, if I want to find NM, well, if ML is 4.5, what is NM going to be? 4.5. And then let's do TV. TV. Now, TV is the whole thing. And I know that that's 3.8. Well, if that's 3.8, what's TU? 3.8, which means TV is 7.2. Okay. Questions on that one? Okay, last one. It's going to be kind of similar to 3 and 4. So let's draw a parallelogram. Except we don't need transversals for this one. All right, so on this parallelogram, let's say the top is 6y plus 1. The bottom is 4y plus 9. The left is 2x minus 5, and the right is x plus 7. All right, so I know we're all really excited to do another systems of equations, so let's see what kind of equations I can write. Now, I'm not given transversals this time, but I don't need the transversals, but I am given all 4 sides. What do you know about the sides of the parallelogram? Right, the opposite sides are congruent. Now, it's not all of them, right? They're not all congruent, but the top is congruent with the bottom. So how would you write an equation with that information? 6y plus 1 equals 4y plus 9, and the other one would be 2x minus 5 equals x plus 7. And we're all geared up, ready to solve a systems of equations. Do I need to do that? No. Why is this one different than 3 and 4? Yeah, exactly right. This first equation just has y's. There's not an x in there. So you can solve for y. You can figure out what y is. Subtract 4y. We have 2y plus 1 equals 9. Subtract 1, we'd have y equals 8, which means y equals 4. And the second equation, it just has x's. So we can subtract x from both sides. So we'd have x minus 5 equals 7, which means x equals 12. So may not have to use systems of equations for all of them.